anyways, hey guys, next week, Saturday will be the normal class, right? Everyone look at this page, look at this time this calendar here, okay? This day is going to be a normal class, right? We are going to have a replacement class on the 21st for the week of February 3rd. I won't be here, right? And then after that, on the 28th, there will be another replacement class on Sunday because of the replacement class for Chinese New Year. Okay, as you all know, Chinese New Year usually we have 1 week break from GTG, right? So happened that this week, right before Chinese New Year, I'm going to go see Sky Full of Stars in Bangkok. Yeah. So anyways, yeah, the next 2 Sundays we're going to have replacement class on the exact same time. Okay. On Sunday, it will just be replacement class for physics for the 3rd February. Okay, hey, listen up, boy. No. On the 21st, we'll be replacing for physics only on the 3rd February because I won't be here. On the 28th, we'll be replacing for physics and chemistry because Kenny on the 10th also will be having Chinese New Year holiday, so he won't be here also.
Wait, no, this is one of the days.
Okay, I'm gonna write this into the group chat, okay? Hi everyone, we will be doing replacement class on the 21st and 28th Sunday for classes missed on the 3rd and 10th February. The timing will be as per usual 12:15.
Only
for 21st physics and on the 28th will be for physics and chemistry. Okay, please refer to the group chat.
So should I skip next week's cross country just to come there?
Yes, you should skip it.
I was gonna say that.
Come to class.
I've done this. Really?
Okay.
So give me.
Don't worry, I'll send you a video later on. You can have a look at it. It's very, very important. I'm going to send you a video. I have a video that I recorded previously, so it will still cover the whole thing. Okay, so anyways, I want to say that we're going to go through a quick recap of what we learned last week, guys. Basically, last week we talked about the alpha, beta, and gamma radiation and their characteristics, right? We said that alpha could be detected in the cloud chamber, and I showed you a video of it. And then beta and gamma is from a Geiger-Müller tube, right? Remember the thing, basically the right, the scanner thing, right? Yeah, something like a metal detector, but instead of detecting metal, it's detecting radiation. Okay. Then after that, in terms of the elements, alpha is a helium. This H is a small e, guys. Remember, it's a small e. It's an element. Beta, it's an electron, 0, -1, and gamma is part of the electromagnetic spectrum. That's why it's a gamma ray. In terms of charges, alpha is +2, beta is -1, as you can see from here and here, right? And because of the charges here, it has a relatively strong and weak ionizing power, meaning to say, 1 alpha particle can steal 2 negative charges from a neutral atom, right? And then beta can steal 1 positive charge from anything else, right? And then in terms of mass, I said you don't need to remember the number, but you need to remember who is the heaviest based on its element once again, right? As you can see, this is the fat kid, this is the skinny kid, and this is the imaginary friend. That's why it's out here. Okay, right. Right, and then in terms of the range, I said that the fat kid can only run a few cm away, the skinny kid can run a few meters, and gamma is unlimited, just like your imagination. Yay. Okay, in terms of the speed, alpha is only 10% the speed of light, beta is 90% the speed of light, and since gamma is an electromagnetic wave, all of them travel at the speed of light. Okay, then after that, we also talked about the penetration power, which is very commonly asked in your exam. As soon as you see the word lead, you should know that they're testing you on gamma. If you see the word aluminium or thick wood, right, you should know they're testing you on beta. and everything else is going to be alpha. Even smoke can stop alpha penetration. I mean, you say smoke particles will block the alpha particles and it will not be able to penetrate through. That's why smoke alarms, they actually have a very small source of alpha radiation inside. Okay, and then in terms of the electric field, which should not be confused with the magnetic field. The electric field is from positive and negative charges, right? Then obviously beta will be attracted towards the positive plate and alpha will be attracted towards the negative plate, as you can see from the pink and the black one here, right? And why did beta deviate more than the alpha again? Yeah, it's lighter, his mass is much lighter, right? So it's easy to push him around. Oh, it sounds like I'm encouraging bullying. Anyways, it's the same for magnetic field as well. In the magnetic field, I said that alpha is associated with what? Alpha is the same like what? Huh? What? What did I say alpha was and what was beta again? In terms of a circuit, what was alpha and what was beta again? Current and electron. Alpha is a current and beta is an electron, right? That's why in this scenario, if we have radiation in the magnetic field, we're supposed to use left or right? Huh? Left, because we are given the magnetic field, we are given the direction of the current, and we're looking for the force is being deviated to, right? And yeah, you can check again now with your left hand rule, you should be able to do this one.
Alpha that's current, beta is
Electron. Yes, correct. Okay. And that's what we learned about last week. Anyone has any questions I want to clarify or not from last week's chapter? Sorry? Oh, it's just the element of the radiation. Helium-42. It is a small e. It's a He42. Oh, gamma symbol is the reverse of Cancer symbol. You know the Cancer, the pink color one that. Yeah, but it's like the reverse. So basically, in my head, I always think that because gamma can help you fight cancer, right? So it's like they reverse the Cancer symbol to make this symbol here.
Yeah,
usually you use gamma radiation for chemotherapy. Okay, but for those who missed last week's class, I'll send you a more detailed video later, but please remain. Okay.
You want to share with us the effects of it.
Okay, this last thing here. Okay, let's go through this. So let's imagine today, right? Today we have magnetic field going into the paper, right? So you can imagine that the north pole is in front of the screen and the south pole is behind the screen. Then I have magnetic field going into the paper, right? In this case, into the screen, right? So then after that, if let's say I shoot three different things, alpha, beta, and gamma radiation in, okay, both all in this direction here. First and foremost, I say that alpha is like current. Good. So if there is current, if alpha is shooting in this direction, the current is also in this direction, So once I have the current and magnetic field using Fleming's left hand rule, show me your Fleming's left hand rule, guys. What? Right, you'll be like this, right? Magnetic field into the screen, current to the right, and then you see that the force upwards. That's why an alpha particle will deviate upwards in a magnetic field, right? But I said that beta is like an electron. If the electron is going in this direction, which direction would the current be? The opposite direction, right? So this is the direction of the current, which once we have the current, once again, the magnetic field into the screen, right? Current to the left this time. Thus, my force finger will be downwards, and that's why my beta particle will deviate downwards. Once again, you notice that it's much easier to deflect or deviate the path of a beta particle because yes, lower mass, that's all.
Lower what?
Lower mass. Mass is lighter. Okay? You will actually work.
Oh, wait, one still because
It felt like it was here last week though. Okay, anyone else has any questions with what we learned last week? This is the foundation for this chapter. You must know everything, boys and girls.
Thank you.
So basically, in this diagram here, this yeah, gamma is not affected by anything. It will just go straight. This one on top is the positive plate and bottom is the negative plate. So if I were to draw you know, like the rails, okay. Yeah, it'll be like this lah. So this is the positive plate and this is the negative plate. Relative atomic mass. Yes, correct. So you imagine like trying to push a really fat kid, right? It's very hard for him to move. Yeah, alpha is the fat ass kid, which you can see from the element itself. Okay, so like obviously this is lighter, right? You look at the composition of the helium particle, there's 2 protons, 2 neutrons already. This one is just 1 electron only. So obviously this one is much heavier, and we know that mass of a nucleus is all in the proton and the neutrons, right? This is just 1 electron, so it's like electron is negatively charged, right? So electron is -1. There's no protons in electrons, Okay. Good. Next, today we move on to the next page.
Yes, brother.
Okay, for the year 11s, right? Whoever wants it, $10. Then no. Okay, everyone. So this is the new part that we're going to learn today. It's a very, very, very easy topic. Basically talk about radioactive decay. So let's imagine today I have a radioactive sample that is very unstable. Okay, let's name it element X. Okay, with 100 nucleon number and 50 proton number. Let's say today I say that this thing is unstable. Okay, and in order to stabilize it, I must decay some part of it away. Okay, let's just say today it goes through alpha decay. Okay, if it goes through alpha decay, what's going to happen is it actually spit out 1 alpha particle, okay, which is obviously helium-4 right? Plus the more stabilized atom, let's say this one is element Y. In this case here, the mass and energy and everything is still conserved. So here will be 96 nucleon number and here will be 48 proton number. Okay, now listen up. Usually this thing here, we call it the unstable parent nuclei. Okay, just imagine that this guy is a crazy parent, right? And then once it vents out his frustration, the kid will be more stable. But in reality, we know that the kid is going to be a psychopath, right? Yeah. So this is but this is the real term. This is what we call the parent nuclei, and this is what we call the daughter nuclei.
Oh.
Yeah, so in reality, what's happening is it's actually decaying the energy out also, so it becomes more stabilized.
The alpha particle is like it vanishes shit out.
No, you can imagine that one thing split into 2, then the excessive amount of energy goes away in this side, and then the stable nuclei forms in this side. Good job. I think so. Okay, so I want to say that this one is the unstable one, and this is the stable nuclei, guys. Okay, usually the daughter is the more stable one. This is what we call alpha decay. Very, very easy. In your exam, what they'll do is you usually ask you to write these 2 numbers down only, which literally is 100 minus 4. If you cannot do this, go die, and 50 minus 2. And if you cannot write 48, you go and die also, because this is not your class to be in. Okay, very, very easy. This is literally 3 marks. You just need to know the concept and you can literally do it yourself already. Okay, so this is what we call alpha decay. There is another thing known as beta decay, which is a little bit more different and a little bit more prone to error for students. Beta. Okay, so let's say imagine today, same example, right? I have some random element A. Okay, this time with 50 and 25. It is unstable. Listen up. It is unstable, right? Then obviously it will go through beta decay all this time, right? If it goes through beta decay, the first thing it's going to spit out is the electron 0, -1, right? Plus the more stable daughter nuclei, which let's say is element B, right? What should I write here? What should I write here? Yes, 26. Good. Everyone knows this. I mean, I tell you what, in your exam, right, everyone knows this, right? It's actually 25 minus 1 to become 26 mark, right? A lot of assholes, they will write 24 here. If I see 24 here, when I walk around later, I'm going to beat you. Yes.
It's an electron.
Yeah.
So will they will be adding electrons to them or
Yeah.
Okay, very good question. Let me explain this in a more detailed version. Sometimes they ask this in your exam also. If today we look at the composition of this this A element now, right? Right now, how many protons and how many neutrons are there? 25 protons and also 25 neutrons, which gives you 50 nuclear number, right? Look at the composition of B. Right now, how many protons are there? 26 protons and 24 neutrons. Right, 26 plus 24 goes to 50 what? Right. So what happens is, right, this decay process in a more in-depth version, right, is actually converting one neutron into one more extra proton. And this stabilizes it. You don't need to know the detail, and quite frankly, I don't know the detail. I only know that the neutron is converted into a proton and stabilizes it. Okay, so in your exam, sometimes they'll ask you this, they'll ask you something like, explain what happens to the nucleus when beta decay occurs. You're supposed to say that the neutron converts into a proton. Okay, and then everything else is very straightforward. 50 minus 0, 50, 25 minus -1, 26. Don't think 24 here.
maybe
The bond police is here. Okay, understand? Very straightforward, very easy. Okay, so if you look at the notes, it's basically everything I've mentioned already. Please copy everything down and start attempting the 3 exercises at the bottom here.
the benefit of absolutely. But the element stays the same, right? The decay.
No, how can it be the same? The composition is different already.
The oxygen now is changing, right? The element like the same.
The element will change also.
So
It will be from X to Y and A to B, right? Once it goes through decay, the element will change.
so the element changes according to
Yeah. Okay. Are you guys all done copying this? Do you guys even need to copy? Okay, good. Okay, so let's look at the first equation. Okay, I'll give you an example of what to do. Okay, so obviously this one here, all of them goes through alpha decay, right? So obviously it's going to be helium-4 here, right? Then the number wise will be 206 and 82, right? And you're asking yourself, what could this element be, right? In your exam, if they give you something like this, you should refer to the periodic table here and find the one that is 82, right? And sometimes, if the most common confusion here, right, is the students like they refer to this 206 instead, and they are looking like, oh, where is 206? Where is 206? Where is 206? Which obviously is not there, right? You can confirm this by checking with known elements. For example, this PO is 84, right? You check at the bottom here, is 84 PO. Oh, yes, then this number on top is actually a proton number. Right, and then from here, I'm looking for 82 right now, right? So 82 this time will be the PB law, which is your lead, right?
One alpha.
Only one. Yeah, only one. Only one. This will not be chemistry. You don't need to balance the equation. It will only be one. Fun fact, guys. 3 years ago, right? They didn't used to like I said, right, they didn't used to ask you to find the element. They only ask you to write the number down. But one night, right, before the exam, I had a dream, you know. I had a dream, serious. It was like a prophecy, man. I had a dream that this year they're gonna change it up a bit and they're gonna ask my students to find the element. Before this, I don't teach them to find the elements, you know, before this version of the notes. So then after that, I dreamt of that, right? I'm thinking, wow, what if really tomorrow it comes out like that? And that day I told my class, hey guys, you know, I had a dream, and then you'll be asked to find the elements from the periodic table yourself. So I'm going to teach you guys how to find it, and then just hope that in case tomorrow it comes out, really that year it came out. Then everyone is like, oh my god, because imagine that year, right? Before that, all the past years, they'll never ask you to find the element. Huh? So then that day when I was teaching, everyone was like, this is just stuff in case of that day really came out. Then it's like, holy shit, Gabriel, Prophet Gabriel. This year, let's see if I have another dream for you guys. Then from that year onwards, I teach my students how to find an element.
Honestly, right, do you find concerning that the IGCSE exam showing up in your dream?
Yeah, exactly. All YouTube, right?
And you could have just come to the random, maybe what crazy sack, but like, you dreamed about.
That's how much I care for you guys.
Wow.
Thank you.
I'm here one day.
Even though I'm only supposed to see you guys in the center, sometimes when I go back, I think about you guys also.
You get
Actually, I only reached the year 10 year 11 students. If not,
oh my god.
start to label pedophile already.
Yes.
Only a year 10, year 11, 10 bucks. What? Jay-Z? She wants it? She can get it for free. What the
Let me tell you a story.
You don't put Jay-Z in? Are you serious? Dude, she's been here for the longest time now. Yeah. Yeah, like that one.
And then she dropped something there and picked it up and she was staring at me. And I looked at her for some time and I was like, I was gonna say something really stupid. But the fucking like she was like, can I get
You see, you know, when she first joined my class, her name is Jay-Z. Then every time she walked in, for chemistry and physics.
Yeah, I know.
Oh, okay, register. Yeah, anyways, every time she walked into the class, I'm like, oh my god, can I get on call? Do you want more cook and raw with it? It's a song by Jay-Z, don't you know? It's so good, man. After the message me. Sure, I knew something. How about a drink? Okay, next week, claim your drink next week. What do you want? Starbucks? Boba?
Slumber Monkey that she just at the.
That right. This year I was thinking, me and Gibu were talking about hosting like a event because this year we did Sunway, right? This year we're thinking go Genting, but we'll be okay if you guys go to Genting and stay with us one night.
Money is the problem.
Obviously, you guys will have to Yeah, stay at night, and we'll probably go to the theme parks and everything. Yeah.
Is it money? I think that what about
Okay, either Genting or maybe somewhere again. Nah, oh, the new one, the Gamuda Land one. You know, there's a new water park by what? I can't remember what's it called, but we haven't been there before. I was thinking to go, or we could all just go karting.
oh nothing. Oh, it's not. I don't think it's 15 minutes and shit.
Okay, we're going to make a poll later, right? And then we see what. Oh yeah, who's joining my team for dodgeball? I don't defeat you in every game.
What? When
Go read the sign.
You go back to yeah, or so we still the bar.
Are you guys done already for this one? Okay, sit down. Are you ready, Andy?
Okay.
wave.
You're when you can write down. Ayo.
This page two. But anyways, this one is a very straightforward. I'm not going to discuss it. If you are, okay, let me just walk around and see how many of you guys.
What? Or I did it buried them.
Also, how to find this fun? I don't think no fault. You would have gathered. Some jobs are cigarette.
We start to make such deals.
Oh.
Like you read the whole side.
See once. Nah, Macy, I can give it to her. He stopped already. Okay, anyways, moving on next. This part is very important, guys. Pay attention to this. This one, if they ask, if they ask about this, if they ask about radiation, most likely they'll ask you to do some form of calculation, which is half-life. Yes, which is associated with half-life the game. Okay, anyways. Basically, half-life is the amount of time taken for some radioactive substance to decay their radiation count. Okay, so what do I mean by that? Sounds gibberish, right? Let me simplify it. Decay by half its current radiation count. Okay, let me draw it out for you guys. Okay, everyone, listen up. Imagine today, right? I have a very radioactive substance. Okay. Okay, and then let's just say the radiation count is through the roof. It's like 1,000 counts per minute. Counts per minute is basically counts per minute is basically the units for the radiation. Yes, shut up. Shut up, listen, shut up. Okay, radiation counts per minute is basically the radiation amount for the radioactive substance. Okay, usually in terms of safety wise, shut up, listen. Shut up, listen. In terms of safety wise, right? Background radiation is about 30 counts per minute. Okay, this means to say, right, everywhere that we go, right, there's some form of radiation which humans are already accustomed to already. will be fine. Hey, if you ask me to repeat this later, I'll beat you, I'll tell you. You better pay attention now. Okay, so if you have 1,000, obviously that's gonna kill you, lah, right? So what happens is, right, usually if something is very radioactive, right, we'll store it in a lead container until it decays away. Okay, and the time for it to decay by half its current amount is known as half-life. So let's say, for example, this radioactive substance has a half-life of 5 years. Okay, it means to say after 5 years storing in a lead container, it will be left with 500 counts per minute. Another 5 years that goes by, will it become 0? No, it will only, yes, it will only half its current amount, which is 250, right? And another 5 years will be 125, and another 5 years will be 6.5. And then maybe another 5 years will be 31.25, right? So wait, let me finish first. So basically, for me, right, the half-life is for me to calculate how long do I need to store this shit before I need to throw it away. You know, like recently Japan, they started releasing the nuclear waste into the sea, right? And after a lot of people say boycott sushi because we're gonna die from radiation, all this kind of shit, right? In a realistic point of view, at least from a scientific point of view, I'm sure the engineers did their calculation like this, and then they said, oh, now it's safer, you can just throw it into the sea, it's fine. But of course, there's a lot of assholes and speculation that say that, oh, these guys are just doing unethical things, which is very common for businesses to do, and say that, oh, we actually finished storing them already, the half-life decay, everything away already, so it's safe to throw it in the sea. So obviously there's two sides of the story. It could be radioactive due to the business nature of business people, right? Or it could be really safe due to the calculation from the engineers. But we'll never know until someone dies.
They just sound like
Yeah, and then they're gonna stop. Actually, they're just feeding Godzilla and just making an excuse to dump it.
One.
Sorry? You have to store it in lead containers.
Oh, because
I mean, they'll wear the lead hazmat, right? The full lead gear, and then they'll take that shit and they'll put it in a lead container and close it forever. No, you can't physically see it. Fun fact, when radiation was first popular, right? America tried to make a very fun radioactive toy, which actually had radioactive materials in the set. Yeah, so what happened was, right, they sold 5,000 units of those toys, which have crazy radiation counts.
what about
Oh, it's basically exploring radiation.
what? What related?
So like there's some, I don't know why, there's some shit there, and then you're supposed to play with it like your you know, like what's it called, the microscope, toy microscope and shit lah, right? So 5,000 sets were sold, all of them died.
What's so funny?
All of them. Right, so yeah. Yeah, what do you want to ask now? Counts are counts, idiot. Counts, you know, like 1, 2, 3 counts. Sorry? Like I said, like you have to wear the full hazmat suits. You know, like no, you have to like this is the radioactive substance, right? You have to put it in a container and you need to seal it. It's a lead container, you know, like the lead drum barrels that you see on the movies, right? Or it'll be solid most of the time. It'll be solid most of the time.
The 5 years, like 5 years is the half. Oh, so that's what you.
But the half-life will differ for different materials. Yes, for that one material it will be constant throughout time, but different materials will have different half-life. Okay, so let's say for example, this thing is stable, right? If it's stable, it will usually have a very, very long half-life. Okay, and if it's like 5 years, it's like relatively short lah. So in reality, I need to store this radioactive substance for 1, 2, 3, 4, 5 times 5 long, right? Which is 25 years. I need to store this 1,000 counts per minute for 25 years. Only then I can release it to the sea and consider it safe. Okay? Somewhere around 30 per minute. is considered safe, which is where we have what we have here right now. No matter where you go, there will be radiation count known as background radiation. It's safe for human beings. We have already adapted to it already.
It will still be
Yeah, it will still decay beyond 30.
maybe key beyond 1 against 0.5.
Just 0.01 may contribute to the background radiation. Because no matter what number you divide by 2, it never becomes 0. So it just like contribute to the background radiation.
Does it the property based on how the radiation
Well,
it is more
properties are dangerous. Just the dangerous. Just the less dangerous.
getting it balanced.
You get a positive negative.
Politic what?
Positive. Yeah.
Right.
Shut up. Okay, start it. So basically, half-life. Okay, usually there's actually a very complex formula that I don't care about. I would just recommend drawing that little diagram. It's easier to see.
Let's divide into every 5.
There's a very complex formula. I looked at it when I started teaching. I saw it, and I thought, whoa, this is unnecessarily complex. I'm sure no one needs to do that, and I just continue doing arrow diagram. So far, for the past 7 years, everyone's been doing fine, no complaints. So I can only safely assume that this method is easier than the calculation method. Okay, easy. Moving on. Okay, if you look at this part here, yeah, half-life can be used to go for carbon dating as well. For example, if I dig out the dinosaurs bones and then dig out the dinosaur bones and then I want to know how old this thing is, right? Usually I'll count how much carbon is left inside and then I'll backtrack the half-life and see how long it has been here already. So let's say, for example, there's only like 6.25%, right? Then I backtrack it all the way until it's 100%. Then I count how many half-life it went through. Then I'll be able to tell how old it is. Okay, very good question. All living things, right? They have 100% carbon count in their body as long as they're living, because we keep absorbing carbon, right? Because we are made from carbon. As soon as you die, the carbon will start to decay away. The carbon is a very stable isotope, so it has a very, very long half-life. So we can, if let's say 50,000 years after I die, right, people will just dig out my bone, count the carbon left inside, and then they'll be able to backtrack and see how old am I. It should theoretically never be 0. It will definitely be very close to 0 because any number that you divide by 2 never reach 0.
That's every element.
Yes, every isotope, radioactive isotope has a half-life. Every radioactive substance has a half-life.
What's the half-life?
I think it was 50,000 years if I'm not mistaken. I can't remember.
Hey.
Hydrogen, no, I don't think so. Hydrogen, not that I know of, at least. Usually they use carbon and radioactive substance only. Okay. Anyone else has any questions? Okay, good. Hi. Pay attention, everyone. So yeah, this is basically everything that I've mentioned. You don't have to copy anything, right? Nothing really to copy. Read through everything and start attempting the 3 questions at the bottom. Oh, you want to watch the video? Sure. Hey. Okay.
Wait, let's say you find that like sorry, it's you, right?
Hey there and welcome to Brain Stuff. I'm Josh Clark and this is the Brain Stuff where I explain to you how carbon-14 dating works. Carbon-14 dating, which we also just call
Carbon-14 is the one that we use to count how long people die. You know, like this one I said, the amount of carbon, you know, this is that.
Carbon dating is a form of radiometric dating. And all it is measuring the decay of a certain type of atom found in a once living organism to determine when it was last alive. And all of this starts in the upper atmosphere of Earth, where it's constantly bombarded by cosmic rays. And one of the things these cosmic rays do is knock neutrons off of some atoms and protons off of others. And before you know it, the nice, stable, family man nitrogen-14 atom is all wrapped up and gone crazy and becomes what's known as a carbon-14 atom, which is radioactive. Now, carbon-14 atoms aren't the only ones in the upper atmosphere. There's also carbon-12 atoms. Carbon-12 atoms are in much more abundance, and they're pretty stable. Carbon-14 atoms are, again, radioactive and unstable, but they're formed at a reliable, steady rate. So at any point in time, we have a pretty good idea of the ratio of carbon-12 atoms to carbon-14 atoms. Got that? It's important. Now, carbon dioxide is essential to life here on Earth. Plants breathe it in, animals eat the plants, we eat the animals and the plants. And these carbon molecules, carbon-14 and 12, that make up the carbon dioxide, get in everything. What's neat is that the ratio of carbon-12 to carbon-14 found in all these living things here on Earth is pretty much the same as what's in the atmosphere, which means it's predictable. And some very, very smart scientists have figured out that carbon-14 actually decays at a predictable rate, right? Carbon-14, like all radioactive particles, has what's called a half-life. Now, the half-life is the amount of time it takes for the number of radioactive particles in a sample to decrease by half. Carbon-14 has a half-life of 5,730 years. That means that after 5,730 years, the amount of carbon-14 atoms in a, say, plant that you found fossilized will be half of what it was the last time that plant took, well, a breath of life. After 11,460 years, which is 2 half-lives, there'll be a quarter the amount of carbon-14 that was originally present. And then after 17,190 years, you'll have just an eighth of the number of carbon-14, and so on until there's none left. And this is actually one of the limitations of carbon-14 dating, that eventually you're going to go far enough back in time that all of the carbon-14 atoms have decayed. And you don't know whether this took place a day before or 100,000 years before, which means the time limit that you can date things using carbon-14 is roughly 50,000 years. But as long as you are trying to date something that lived on Earth within the last 50,000 years, you can figure out roughly when it was last alive. And the way that you do that is by measuring the rate of decay of carbon-14 atoms compared to the slow and steady carbon-12 atoms that are also present in there. Presto, changeo, you've got some carbon-14 dating, and all of a sudden you say, oh my God, this wooden axe handle is 12,000 years old. Pretty sweet stuff. And this whole thing gets even more interesting.
Okay. Read the question for these 3 questions and start attempting. You'll find that question number 1 and 2 is very logical and you will probably not need to think much about it. Question number 3 is the relatively more challenging one. Let's see how many of you guys get it right. Wrong again, really. That's wrong, really. Looking for their friends. These 2 are given talking about the spot and experiment, but the method they use you better check figure as it is.
We try to not have one software. And not software. We
Really, but probably.
half detail of the after that half detail of it is one software. As we say, they come in 3 4 decay.
The first step, one.
Second one. Oh. What time is it? But it was 3. Yeah, before. I think you draw that everything will be better for you. It's just see you go to the car. And we see the pan so moving. Tag long. It fix it. Well, pitch. It is not right. See, so we did they were very well. I'm not see. So yeah, the was for counting for we can money. Yeah, like all things that we able to do. What we always know from your things on the savings, what we did for that. You're not going to apply the good. Oh, yeah. Oh, I don't. Oh, the I don't think of any. Yeah, but. Then, like it, share one. One day, but. Okay, the reason I don't know why. You're sorry. Yeah. Yeah. Well, and that's the understand. Good for your business, great, like, yeah. They are all in this evening. This back, but. Fashion things. That's that thing. Yeah. The rest of the cost only the necessary. Yeah. Okay, the formula. Well, great, self is needed, so yeah, we see it. So, Matt, we are. Check. Yes. Very fun. Well, it's really good. Yeah, very good. Oh, oh, see you. What would you? Okay, come here. Come with I'm surprised you didn't get it. Ain't no obligation to that. So,
Let's go through the answers, right, guys, since most of you guys are stuck at question number 3. The first 2 correct lah, which is obviously going to be 104, and the second question is not the same, it's 304, because this would have decayed away, and this one is not decayed away. Right. So the first one is 104 and 304 lah, right? But the third question is where things get a little bit more realistic to your questions. Right? It says that a researcher has 200 counts per minute at midday. What time is midday, by the way? It's 12 o'clock. And at 3 o'clock, he has dropped to 25 counts per minute. So I know that it starts with 200 counts per minute and it ends at 25 counts per minute now, right? This was at 12 o'clock and this was at 3 o'clock. If I go through half-life, 200 becomes 100 and 100 becomes, and 50 obviously becomes 25 lah. If you look at this question here, right, how many half-lives did it go through? 3 half-lives in a span of how many hours? 3 hours. Then obviously one half-life would have been equals to 1 hour, right? And thus, if you think about it, this was 1 o'clock, this is 2 o'clock, and this will be 3 o'clock. Ta-da! Okay, guys, the last thing I want to talk to you guys about, not the last thing, actually, there's a few more. Okay, so this type of questions will actually come out in your exam, which is quite straightforward. You need to just do the half-life, divide, and eventually you'll be able to find the half-life, right, the duration. But in reality, usually they'll give you something a little bit more complex, like this.
What is the half-life?
Shut up, lah. I used to, during the MCO days, I tried to do half-fun presentation. But a lot of students, they say they prefer watching my poorly drawn illustration compared to the PowerPoint, and thus I stopped using it. I actually put so much time in this illustration, you know, like, but oh well. They prefer my...
I think it sounds like you should
I rest up.
Has to be covered. So this to like ladies and gentlemen, what's a great quick. Sorry.
Nah, not right now. Okay, anyways, if you look at this question here, guys, can everyone read through this question? Actually, everyone that's here right now, can you attempt this question and tell me what do you think the answer could be? I'll reveal the answer in 5 minutes. Huh? It's not a decimal, it's a whole number. 40,000. I must emphasize that there is conclusion in this question. And I also want to hint that magma radiation does not go through half-life decay. So it's a constant? Yeah, it's a constant.
Great.
Think about it, everyone. I'll give you the answers.
Yes. Okay. Really big.
Okay. You want to see exhausting things. Good.
Or
You're right. I think 5. At least.
So I think the kind of people
Much. Yeah.
That's what's
What's the answer? What? That's wrong.
after you get spouse, like, say, it's okay, the public, like, it's terrible. So that you take for them, I'm not telling you that, so. Yeah. And this is on the back, that there's a background of the. Yeah. It's always really important.
Yeah, yeah, very good. Things don't feel hey, appendix might be. You know, then.
It's not pure really, it's not pure.
But it is like. How many, and you guys do buy weight roll of the, right, away. Don't get by something, but if you guys find that for me, you would like, if you only like. Different stuff, kind of tired. Sorry.
Voice on excellent on the very fast. Oh, you. Oh. I think that I'm over it. And you like that. The people are actual kids. I didn't have to think of both of them. And I used the oil. Oh, I just want to show that there's nothing here. And then the next page will show you that it's actually whether the substance is here is the oil. And we had never thought about it. The man, I said
Like the number of minutes in like 24 days, right?
yeah, that's wrong.
What? 24 days is very fast, really.
Okay, guys, let me tell you how to do it. Okay, guys, so if you look at this question here, right, there are a few key things that you definitely have to look at, right? First and foremost, they say that the background radiation is 40 counts per minute. Okay, and then they say that when I bring this sample close to the detector, right, it reads 200 counts. This 200 counts is actually inclusive of the 4D and also the radioactive sample. So in reality, the first thing you wanted to do was to find the radiation count for the radioactive sample, which is 200 minus 40, which will give you the 160 here. This 160 is the one that goes through half-life decay, right? So in reality, it will be 160 to 80 to 40 to 20 to 10, right? But I want to find when the radiation count is 50 counts per minute. If I just look at this, right, none of this is 50, right? Do I take a random guess? No. Once again, I want to emphasize that whatever this detector reads, it's inclusive of the background radiation. So in order for me to get 40 counts per minute, right, it's the radioactive sample plus the background radiation, which in this case here, the background radiation is already 40, right? The radioactive sample has to be 10 for you to reach 50. So in reality, this was our final destination, guys. Right, which they say that how many half-life went through here? 1 half-life, 2 half-life, 3 half-life, 4 half-life, right? 4 half-life took a span of 24 days. Then obviously 1 half-life would have been 6 days.
I think the second one is good like that. But
Oh, the DLC that
What? Do you understand or not? Seriously, you need to. These kind of questions always comes out in your exam. If they ask. If you're lucky, they won't include background radiation, then you just divide 2, divide 2, divide 2, divide 2. But if you see the question, they already mentioned that there's half-life or there's background radiation, right? Then you must include it in your radiation count here. Okay,
The,
good. Want to have a look at another example question?
Will this be the
Yeah, this will be the relatively harder questions. Okay. Okay, good.
Telling teacher. I'm telling my older sister when just ages. Well, we're telling Sunda. Yeah. In any word, didn't teach.
So, the teacher said that we're going to be taking with the half years.
It will be a little bit different because they included space here and a few more extra things here and there.
Oh, space is the relative thing.
Yeah, for sure it'll come out this year.
Space.
Very good time. Space and what's it called? Absolute zero will definitely come out. Either in paper 2 or paper 3. Yeah. Either in paper 2 or paper 4 only. Actually cannot find the question. Hey, everyone look at this question. Yeah, this one. Tell me what's the answer. Think about it. Exact same way we did it just now, but slightly easier. Very good. Amazing. Amazing. Fast. This guy already got to. Huh?
Oh, quantity plus. Okay, 670.
Yeah, very good. Yeah. Oh.
No, quantity plus particle. Really, that's wow. I'll go for all of those. Very helpful in the shirt.
Yeah, that's why I said it. Did that? It's not this. Hey. Hold on. Okay.
Answer is donkey, guys.
Do
you get it? Excellent. Very good. Okay, guys. That's gonna be it for today. Hope we'll get this week. Go to the next week.
Okay.
So, we get to stuff that we have knowledge to serve. You don't. I have done kind of back in much at and the part of there's so much new. Yeah, the young children, yeah. Because then, yeah, poverty compare. Well, this is what this. I got plenty of time and put up there with that. Oh. It's that yeah. I think I would be some that you would. Well, it's not practical. So, I was trying to have a so now. When it's like what? What? Well, We could. Oh yeah, I'm not gonna push all the back. Is. Or. So. What's this? That. Yeah. She did do. Well. I want, I want. Everything there. Oh, wait, I don't know this. And now what? I want to be everything. I don't know. Okay, good. Well, you mentioned that. I can take that right now. Oh, you. I go back to mobile back to like shit. You want to take a that thumb? But you're speaking at the bottom. You could have spoken. Look at this. Why is that a stick? Now feels good. It's a team to let you find out the game. I'll take it for a little for. Let's play it. And I can still remember, I guess, without my job. I could give me a problem. And I think the company all and like well, who's that? Still nobody is name. It's silence. I think balance is rather. Why is everyone having sibling with all of them? Don't be stupid, I like this, you know, this is lack of studies. Yeah. Oh, how you see it. Do that. No. I I'm a baby. No, it's comparison. See what? That you go. I don't think you see about it. Something that don't define for replacement. Okay. Ball,